Hi, this is a homework video on problem 17 of lesson 10.3. The question is written on the screen before you. You are given a parametric relationship, x equals cosine cubed, y equals sine of theta cubed, and you are to find the first derivative, the second derivative, and evaluate both of those at pi over 4. So I need to remember that in order to find the first derivative dy dx, I am going to differentiate with respect to my parameter, the part of the equation that is the y equals. I need to remember that this notation here with the 3 really means this. So chain rule is something that applies because I have a composition of functions. The 3 comes down in front. I have sine squared, and then I need to take the derivative of the inside function, which is sine, and the derivative of sine is cosine. Again, with the x, I need to remember that this notation actually means cosine of theta quantity cubed. So again, by chain rule, 3 would come down in front. I'd have cosine squared, and the derivative of cosine is negative sine. So I put the negative in front, personal preference. Then I can look at this and see a number of things will make ones. So 3 divided by 3 is 1, cosine over cosine, sine over sine. And so I am actually left with a negative, or an opposite symbol, and sine over cosine, which is tangent. So my first derivative is negative tangent. To find the second derivative, I want to differentiate what I just found and then divide that by dx d theta. So my second derivative, I'm going to take the derivative of negative tangent. So I'm going to have negative secant squared. And then the dx d theta, I can actually just look back in my previous work and grab that again, pre-canceling. And then the negative and the negative will make a positive. And then it's sort of personal preference how you end up writing this. I feel that the most consolidated version of this would be to smush either all of those secants into the cosine at the bottom or all of the cosines at the bottom into the secant at the top. And I'm going to go with the secant route. I'm not really sure why, just in the mood. Okay, and so that would be my second derivative statement. The last part of this question was to evaluate each of these at pi over 4. Okay, so notice my notation here. I don't want to just write dy dx equals sine because I'm actually evaluating at a particular location. So my notation for that is a vertical line, and then I have like a little subscript-ish type thing here where I'm denoting that I am letting theta only equal one particular value of pi over 4. And so then I can just substitute in, and I do that because it's not function notation that I'm using. I'm using Leibniz notation. Okay, and then tangent at pi over 4 is 1, so this would be negative 1. And then for my second derivative, same kind of idea. I'm evaluating at a particular location, so I'm going to denote that in my writing and write that I'm doing this at pi over 4. And then I'm going to just substitute in. So I'm looking back here at my black writing. And I know that secant at 45 degrees is going to be root 2. So this is root 2 to the 4th. And then down here I'd have 3. And I know usually we say root 2 over 2 for sine of pi over 4, but I think it's actually easier in this problem if I think of the non-rationalized version, 1 over root 2. It's not impossible if you didn't write that. Like, it's totally fine. You can figure it out. I'm just trying to be efficient. And then I took 10 seconds to explain my efficiency, which therefore cancels the efficiency. Okay, anyway, so this root 2, if you square it, becomes 2. So to the 4th would become 4. This radical 2 in the denominator here, if you think about dividing by a fraction, that's multiplying by a reciprocal, so the root 2 would go to the top, and the 3 would still be in the denominator. So that's my non-decimal exact value. Okay, I hope that helped.